Test. Alright, so this should be streaming, but it's going to take me a second to confirm that YouTube is being a little weird. Sorry about that. I'm just waiting until I can see the stream myself, basically. Well, I have no way of knowing right now if anyone is watching at the moment, because YouTube just is not being kind right now. Oh, maybe this is what I want. This is what I want. Awesome. So I'm going to do something that might cause feedback, but I'm going to do it very briefly. Test, 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 test. Okay, so I think it's working. Yeah, okay, so it seems to be working. What I plan on doing, which I'll probably repeat a few times, hold on a second. Sorry, I had to clear my throat there. What I plan on doing... Well, anyway, what I plan on doing is I have these lecture notes that I've used for business calculus before, and it's not identical with the material in the online course, but there's a lot of overlap. So what I'll probably end up doing is I have the module 7 in front of me. It's loading, now I'm looking at it. And I'll just go through this document, and I will find, oh, this problem is a lot like one that's here. So I'll go ahead and do it. Or maybe I'll just do all of them. We'll see. Not a lot of time was spent on limits in the online class, which is fine. It's not supposed to spend a lot of time on it. But I want to spend more time, rather than presenting the concept of limits, because most of you've already watched a video or read about it, so you understand more or less what limits are. I'd rather focus on 7.3 and 7.4 because that is what's going to use limits to calculate things. So anyway, I appear to have one viewer now, and I hope the sound is okay. You can type in the chat to let me know. Oh, hold on. I need to do something. You can type in the chat to let me know, oh, the sound is way too quiet or whatever, which may be the case. I'm trying to speak into the microphone, not next to it. So let me know if the sound is not okay. So I'm going to go through this document and just find a problem, unless someone puts in the chat asking, it's being kind of annoying. Well, I need to full screen it. Yeah, okay, there we go. I'm not sure if the video quality is that good. I should be streaming in 60 frames per second. In fact, let me... Yeah, the quality on my screen is not good. So, let me do this. I'll pull it up on my phone so I can see it there. That might be a better indicator. Sorry about the fixing things as I go along. I had some technical problems when I got here, so I had to fix those first. Oh, there we go. So I want that. And yeah, okay. So I'm going to see how the quality looks. And I'm going to turn the volume down. I'm going to see how the quality looks on my phone. And then I will proceed with actually working out examples. So I'm going to see that viewer count pop up. I guess. Come on, Windows, don't fail me now. Sorry. Yeah, I guess the quality is fine just on, anyway, when I'm in the creator interface, it just looks terrible, but yeah, it looks fine on my phone. Okay, so I'm gonna go ahead and I'm gonna do I'm gonna walk through this first page and just as a reintroduction of limits, just in case the one person watching didn't really understand it, just in case, and then I'll go look for, here are some problems that are somewhat similar to the ones in the Blackboard. So this first thing I wrote so that someone could just read it and it's all there, but I'm just going to sort of review it briefly. If you have a function like this one, like f of x equals x squared minus 4 over x minus 2, well, you know, functions have inputs and outputs, and you can put in 0. What's f of 0? And you would get negative 4 over negative 2, which would be positive 2 when you divide as a result. And you can put in 1 and 10 and whatever numbers you want. But when you go to plug in 2, you get this weirdness where f of 2, you plug in 2, and then you get 4 minus 4 over 2 minus 2, and you get 0 over 0. Well, what is 0 over 0? I did say I'm going to go over this briefly, but it might be a little long-winded, but I think that's fine. I want to talk about why this is a problem, 0 over 0. Like, because you could say, well, why isn't it just 0? Or why isn't it just 1? Right? Why not? So I want to talk a little bit about what 0 over 0 is, and I'll try to be brief. So I'm going to use some empty space over here. When you have a division, I'm going to use a thinner marker. When you have a division statement, 8 over 2 equals 4, right? Well, why is that? Well, because 2 times 4 is 8. That's the underlying reason. When you learn division, you learn it in terms of multiplication. So the reason for this is 8 equals 4 times 2. I've multiplied the 2 to the other side in a certain sense. But this really is not an algebra step. I'm just saying what it means for 8 over 2 to be 4, that there's a multiplication that corresponds. So if you say something like, well, 0 over 0, this equals 0, and in fact, what I ought to do is I'll make the offending 0 red. It stands out. This is the one that might be the troublemaker. So if I say that 0 over 0 equals 0, well, okay, well, if I rewrite this, this will be 0 equals 0 times 0, which is true. It's just as true as this. Sorry that the screen jumps around a little bit. I might be able to fix it. I don't know what it is, but OneNote's a little fidgety, where you undo something, it wants to move the focus of the screen. But drawing in the corner seems to fix that. I don't know why. Anyway. Excuse me. I'm trying to clear my throat into the microphone too much. So, what about, by the same reasoning, could we say that 0 over the offending 0 is 1? Would that make sense? So if I do the same thing, I say, well, what's the multiplication statement that corresponds to this that would confirm or deny that this is fine? Well, we end up with 0 equals 1 times 0. What's 1 times 0? Oh, it's 0, isn't it? So these are both true statements. 0 is 0 times 0. 0 is also 0 times 1. So if we take these as being the justifications for the division statements, then they're both equally true. And you could do that with any number. I could say, okay, 0 over 0 equals, let's say, negative, I don't know, 29. Pick a number. And I rewrite this using the rearrangement into a multiplication statement. Well, 0 times negative 29 is 0. So this is a perfectly valid number to say is what 0 over 0 is. If that's what you want to do, you want to have a number for it, you can use the same reasoning for any number. And generally in math, when a line of, well, generally in logic, I suppose, if a line of reasoning works for any answer, that means it's not a good line of reasoning. It's like, that's not going to work for this example. So when we try to say, trying to undo here, yeah, it keeps moving. Well, I'll try erasing rather than undoing. Anyway, when you try to say what 0 over 0 is, or is supposed to be, you really don't get anywhere. So this has a special name. This is called an indeterminate form. indeterminate form. And it's indeterminate. You can't put a value to it. You're stuck with, we don't know. Arithmetic doesn't really work that way, or it doesn't work nicely. I'm sure someone studies or has studied. I'm certain someone has studied. Well, how do these things operate if you try to put rules on it? And I'm sure someone's done that. But we're not going to do that. We're just going to say, well, that means that we can't assign a value. So for this function, we get 0 over 0, and it should be something. I mean, I guess I should say that we're kind of doing that now, aren't we? We're saying, well, what should this be based upon what it came from? The function it came from can tell us what we're supposed to be getting. And if you do this numerically, if you make a table of values, okay, and you say, okay, I want to look at what does the function do when you put in numbers that are close to 2. So if you put in 1, you get 3. If you put in 1.5, you get 3.5. If you put in 1.9, you get 3.9. And the more 9s you get, it turns out the 9s that you use will just be repeated in the output, and the 1 and the 3 will persist. So it sure looks like when you're putting in numbers less than 2, the result is just 2 more than that. Whatever you put in, you get the result is 2 more. You're adding 2. And then when you put numbers that are greater than 2, like 3, well, you get 5. Hey, that's plus 2, right? 2.5, 4.5. Hey, that's plus 2. Excuse me. So as you put, 2.1 gives you 4.1, 2.01 gives you 4.01, and as you put in more zeros before you put the 1 down, the 2 and the 4 persist, so the output's always just 2 more than the input. So while the function itself does not have an output for 2, it kind of seems like it ought to be 4. And that's what a limit is. What should the function be doing? And you infer that based on the behavior from numbers less than 2 and from numbers greater than 2. You can do this numerically, and it's usually fairly effective, but there are limitations to that, which we'll get to. Specifically in 7.4, tangent lines and derivatives. What if you don't have a 2, but you have an x or something? How do you handle that? Well, we're going to, not do it numerically. You can't do it with a table if you don't have a number to base it on. But this is the concept. You look at the behavior. And there's another way, which is what we will do when we have a variable, is if I have this function, I have this function, this is the one we've already looked at, and I factor the numerator because the x squared minus 4 is a difference of squares. It's x minus 2 times x plus 2, or as I have not written but typed up here, x plus 2 times x minus 2. So I can factor that. And, you might already have noticed or be thinking, well, we can just cancel that out. It just goes away, right? Well, I put a little question mark over this equal sign for a reason, because it's not quite so simple. It is effectively what we do, but it's important to know that there's a lot going on under the hood when you cancel the x minus 2s. They're not numbers. They're variable expressions, so it's not so simple. And you have to be careful when you're deleting or canceling or removing something that could be 0, because when you plug in 2 for x, right? Well, this would be 4 times 0 over 0, which would be 0 over 0, which is undefined. But when you put in 2 here, it's just 4. So obviously, I think, this equation doesn't quite hold up, because when you plug in the number 2 for x, it's false, because you would get 0 over 0 equals 4. And as we said, 0 over 0 doesn't have a defined value. It's just that in this case, we're going to assign it, we're not going to assign it a value. We're going to say, well, the function really should be giving us 4. Is what it should be doing. It doesn't, but it should be, which means that this equals is not quite a genuine equals. It's a shortcut of saying, well, we're going to get rid of the part that prevents us from knowing what the function should be doing. It's an algebra way to get the result that we got from this pattern of numbers. We can do it algebraically most of the time as well. And this is, next part's just basically what I've just said, so I don't need to say it again. If we look at the 2 graphs, here is the original function, f of x equals x squared minus 4 over x minus 2. And you can see I've intentionally put in this little gap there because the function is not defined for 2. This is x coordinate 2, y coordinate 4. And our function is not defined there. So you have a little gap in the graph. There's no point there. And excuse me, on the right, we have the function f of x equals x. Well, I should call it, say, g of x. Right? G of x equals x plus 2. It's some other function. And I think you can see they're very clearly basically the same. But the graph on the right, if I try to put a point here at 2, why is it still red? Sorry. If I try to put a point here at 2, 4, that's a genuine point on the graph of the function. The input 2 does give you the output 4 because g of x is x plus 2. So the output is merely 2 more than the input. Whereas f of x does something a little more complicated. It does not just add 2. It squares your number, subtracts 4 from that. It also takes a copy of the number and subtracts 2 from that, and then divides them. It's a multi-step process. This is a single thing, which turns out, if you never plug in 2, these are equivalent. They're the same thing. Which is why when we take this left-hand side here, the factored, excuse me, the product of the 2 binomials over the binomial equals this other binomial. Binomial meaning 2 terms to the expression. We treat that as equivalent because they mostly are. And again, things are going to get a little bit more complicated when it's not that we're concerned with the input 2, but we're concerned with other inputs, and then there's a variable involved, and you can't do it numerically. So that's just the overview of limits. So that's basically 7.1 in Blackboard. This is just the overview of how you do that, and there are specific examples. I'll do a couple of them, using algebra to work out what that value should be. So I don't want to do a bunch of numerically. I just don't want to spend time on that. It is a bit tedious. So I'm going to skip that. I want to find one that's done algebraically. And all of these, if you're watching, you're seeing these, Theorem 218, Theorem 219, Theorem 2110. This is stuff that's all in the textbook. Not under the same names, but roughly in the same order that the textbook provides it. So here's some really simple examples. When you have a polynomial like this quadratic and you're finding the limit of a polynomial, you can always just plug the number in. That's always going to work because polynomials behave really nicely. That's a somewhat common term in math. You're talking about functions. You say it behaves nicely if there aren't a whole bunch of rules about it. You just do what kind of makes sense. Oh, just plug in the number. The limit is, you just plug in the 1 and you're done. So since the x is going to 1, I'll just plug in a 1 into both places where there's an x. So I have 1 squared minus 1 plus 1, and you total that up, and you get 1. Because of course, these two cancel each other out. So you get 1 as a result. That's it. That's the limit. You don't need a table. You don't need to factor anything. You just plug the number in, and that's it. And polynomials always work that way. Here's one that's a tiny bit more complicated. It's more terms. The input's negative, so I have to be careful about whether the result of one term is positive or negative. So I'll just plug the number in. This is a polynomial. You just plug it in. So 3 times negative 2 cubed minus negative 2 squared plus negative 2 plus 2. And then I can work out what that is. So negative 2 cubed, that's negative 8, times 3 is negative 24. Negative 2 squared, that's 4, but I'm subtracting it, so minus 4. Plus negative 2 is the same as subtracting 2, so minus 2. Plus 2 at the very end. And then, of course, these 2's will cancel each other out. So I really am left with negative 24 minus 4. So I have negative 28. Again, it's a polynomial. It's relatively simple. You just plug the number in, total it up, and see what you get. So I'm going to look for some that require a little bit of algebra. I'm not going to do all of these. I could, but it would just be time consuming. This one. This is the one that typically in in-person lecture I would review this one again and point out, hey, that first example is an example of this kind. But we just did that, so I'll go ahead and do this one. One thing that you can or perhaps should do when you have a limit that's going to require some sort of cancellation, which this one appears to, probably, I mean, it's exactly following that, and this remarks is basically reducing a fraction does not affect the limit, which is what reducing this fraction means. You're reducing it and the limit does not change. Sometimes you don't need to do that. As a quick example, what if I had the limit as, let's say, x goes to 1 of x plus 1 over x plus 2. Well, if you plug in 1, you don't get a 0 on bottom. That's not very well written. I will fix that numerator. So x plus 1 over x plus 2, you plug in 1, you're going to get 2 over 3, right? No cancellation needed. So when you have a rational function where there's no cancellation possible, well, then you're not going to need to cancel because you can't. Even if cancellation were potentially possible, as long as you don't get a 0 on bottom by inputting that number, then you can just do that. There's no need to cancel. Whether it's possible or not, it's not needed if you're never going to get 0 on bottom anyway. Also, what if I did this? What if I did a similar limit as x goes to -2 of x plus 1 over x plus 2? Well, if I plug in -2, the top is going to become -1, right? -2 plus 1 will be -1. So that's the numerator. The denominator, well, -2 plus 2, well, that's 0. So I'm going to go ahead and write -1 over 0. This is not an indeterminate form. This is just undefined. You can't divide by 0. The exception is, well, if you have 0 over 0, that's an indeterminate form, so it's more complicated than just you can't do it. It's, there's a limit involved. But for this one, you can't. There's no number. If you were to say, oh, okay, so this equals some number, right? Well, that would imply that -1 equals some number times 0. Like, if this is a thing you can do, then there must be an equation like that. But there's no, no, it doesn't work. Right? NO doesn't work. So you can't. So for this one, I'm not even going to say that it equals anything. I'm not going to say that. Instead, I would not necessarily say all this, although I would probably think that as I'm thinking about, oh, how do I do this? This is the thought process. I would just write DNE. Does not exist. This kind of looks like an O, so it kind of looks like I'm writing 1. No, DNE does not exist. That's the the answer, if you want to put it that way, for this limit. Does not exist. So if you're going to plug in a number and it just gives you a fraction like 2/3, well, then you can just do that. So what you can do, and maybe you should, is just plug in 1/2 and see what happens. If you get a number, well, good, you're done. You got 2/3, you're done. If you get division by 0 that isn't allowed, like 5 over 0, well, you're done. There's there's limits at infinity. There's one-sided limits, but we're not there yet. So we're going to defer that. But if you get 0 over 0, oh, that means that I need to cancel something, and I should be able to get a number. I don't get it through this way, but I should be able to get one. I'm going to skip that, and we're just going to try to factor. The limit itself kind of gives a clue as to what the factorization probably is. If anyone asks, I can go into, if you put in the chat, why is the 1/2 important? I could, explain that a little more carefully or thoroughly, but I'm just going to go ahead and just factor the numerator and the denominator and then see what kind of cancellation I can get. And when I write this out, when you're working these out for the MyMathLab or whatever, you don't always have to use the best notation every time because no one else is looking at it. But I'm going to use the most appropriate way to write things because the whole point is someone else hopefully is looking at this. So whenever you go to do a change like factoring, you need to write that you're doing a limit every time. It might feel a little tedious, but you kind of need to do that. So now I'm going to go ahead and just factor that numerator. So these numbers aren't too big, so I think, well, I know that. I wasn't going to explain this, but I guess I will. I know that I'm eventually going to have a factor of 2x minus 1 because when you put in 1/2, to 2x minus 1, you get 0. And 1/2 is the number that we're concerned about. So I'm guessing 2x minus 1 is the factor that's going to cancel and go away. If you had x going to some other fraction, basically you have the denominator is that first number, and the numerator is that number. And if the one had been a negative over here, if this had been -1 there, then this would be positive instead. It's just the opposite. So basically you're building an expression that plugging in 1/2 makes it into 0. That's why the limit needs factorization and cancellation for that reason. So I just am inferring that's what's going to happen. Now, since I have a 6 here, and I already have a 2 here, well, I know that the first number in the other one is going to be a 3. The other factor, I should say. So 3x, and since I have a -2 here, and I have a -1 here, well, that means I'm going to have a 2, 3x plus 2. And then the bottom is done very similarly. I'm expecting 2x minus 1. And I'm getting a little ahead of myself. I should probably check. Oh, 2x times 2 is 4x. I'll just write it real big here. And -1 times 3x is minus 3x. And when you combine those, you do get plus x. So that's just confirming that the factorization is correct. Using the 1/2 to build the first factor is a nice shortcut, but that doesn't mean it's always going to work. So checking it through this method is probably a good idea. So in the bottom, in the other factor, I get x minus 5 by looking at this guy and seeing what I already have used here. X minus 5 is what I'm going to have. So then I can get rid of those extra factors. So I'm going to write limit as x goes to 1/2, and I'm just going to not write the repeated factor. That's going to go away. So 3x plus 2 over x minus 5. Okay, and this equals is a genuine. These two things are equal, and the reason for that is we don't have it yet, but this whole thing is a number, right? It's what should that original function be doing when you plug in 1/2? And if we get a result, it will be a number. So this is a number the whole time. And the cancellation, when I got rid of the 2 copies of 2x minus 1, that shouldn't affect that result at all. That should have nothing to do with the number I'm going to get at the end. I mean, it's sort of indirectly related because I'm talking about this problem that I've typed up ahead of time, this limit problem. So, okay, it's fine. It's kind of related, but canceling it doesn't affect the result. Well, let me put it this way. Well, let me rephrase that. The 2 and the 1 come from this 1 and 2, so yeah, I guess fine. Okay, it's related, but it doesn't affect the result that I'm going to get at this point. I just proceed without it, and I'm going to get the number that the first original expression, this guy, was equal to the whole time. I just didn't know it until I worked it out. So when I plug 1/2 in here, well, 3 times 1/2, so it's 3/2 plus 2. I could use decimals if I wanted to, so I could say 3.5 plus 2 maybe will be convenient because we're, that's wrong. 1.5 plus 2. I was thinking about the sum already. 3/2 is 1.5, so I'm just going to use decimals because it's just convenient in this case. So then I can have 0.5 minus 5. So this is going to be 3.5 over negative 4.5. And so it's 35 over negative 45, so this is going to be negative 7 over 9. And there's the result. This is the number that original problem was equal to. The original expression, the limit, was equal to this the entire time. I just didn't know it until I calculated it. But we had a number the whole time, and canceling out these factors had nothing to do with what the number was really. It just helped us find it. Basically, those 2 factors were obscuring the answer. Right? That's what these factors are what was causing or would have been causing, if we had done it that way, would have been causing 0 over 0 to appear. Because when you plug in 1/2 to either of these factors, you get 0. Okay, so that's it for that one. We don't have to do a whole lot of these because I think maybe the idea is clear. I'm going to take a quick look on Blackboard. I'm pretty sure I know what, I'm pretty sure I remember, rather, what this is referring to. Yeah, okay, there's basically two interpretations of what to do here, and I think I know what, the titles are referring to. So, here's an example, not a bad one. And we'll do a lot of these visually, just because the visual concept is more important than calculating numerically, although you can. This says, find the limit as x goes to 1 of 1 over x squared minus 1. So if you plug 1 into that, 1 over 1 minus 1 is 1 over 0. Hey, that's just undefined, right? That if... OneNote's being annoying again. If you plug 1 into x, right, then you're going to get 1 over 0, which is... And it's not equal to 1 over 0, right? So you get nothing, basically. But if you look at the graph, which if you think about it, having a graph is a bit like doing this numerically. It's just that the pairs of numbers are represented graphically rather than numerically. But it's the same kind of information. You know, what input corresponds with what output, and this is just a visual way of doing it. If we think about when we did that first numerical example, I had this table of numbers, and we looked at numbers less than 2, getting closer and closer to 2, and looked at the outputs of those, and say, oh, well, it sure looks like we're just adding 2 the whole time. And then we looked at the other side of that table of numbers, and I said, okay, well, what if we're adding numbers that are inputting numbers that are greater than 2, getting closer and closer to 2, so like putting in 3, 3.5, 1.5, I'm sorry, 3, 2.5, 2.1, 2.01, right? Well, that's what we're going to do here, just visually. Here I have x equals 1 right here, right? That's the vertical dashed line, x equals 1. And it's a little bit hard to see just because this graph is so vertical, so it's hard to zoom in without chopping half of it off, but we are considering left and right individually, so let's do that. I'm going to ignore this bit over here. We're just not interested in -1. I'm going to start right about here and think about traveling along the graph with the x coordinate getting closer and closer to 1, and thinking about what the output value is doing. And I would say I would describe it as the output value is becoming lesser and lesser. It's becoming a larger size negative number. So here we have roughly -2. Here we have -2.8. Here we have -4.2 or 4.3. Yeah, OneNote is being annoying, but that's unavoidable right now, I think. So really what I'm looking at is the y-coordinate, the output, is going to -infinity on the left. So I would write, and I'll do it here, although I might do it up another location as well, the limit as x goes to 1 from the left. And there's a little, it looks like an exponent. It's not an exponent. It's called a superscript, which is, you know, anytime you see any kind of little, you have a thing and there's a little thing next to it there, that's a superscript. Exponents are a particular kind of superscript. This is not an exponent. Kind of like when you have an inverse function, which I think you guys did. I'm going to skip that because I don't quite remember for certain. I don't remember how much time was spent on that. But I guess I could check. Let me look real quick. If I can find it quick enough, then I'll go based on that. Functions and graphs. Vertical line test. Piecewise functions. Yeah, you guys we didn't do... I'll check module 3. Basically, I teach several versions of this course, and some omit certain things. Yeah, you guys didn't do inverse functions. That's fine. Not a big deal. We'll just skip that. Anyway, this is called superscript. So this little minus sign is basically, it has nothing to do with this one, not the result of what the y-coordinate is doing, but that has to do with coming from the left. I'm coming from the left, which is the negative direction of the coordinate system. I'm coming from where the negative numbers come from, right? Like I'm starting at negative infinity and moving toward 1, okay? So the limit as x goes to 1 from the left is 1 over x squared minus 1. Yeah, pretty sure that's right. Equals negative infinity, okay? The left-hand limit as x goes to 1, or the left-sided limit as x goes to 1, is negative infinity. I mean, we determine that visually. Now, if I look at the top half of the graph, and I come at 1 from the right, from the positive direction, you can probably guess what the little superscript is going to be. Well, I can follow these values and say, okay, I'm here at 1.4 roughly. I could start farther away. Let's do that actually. Let's say we're going to start here at x equals 3. All right, and we're moving from right to left. And then here I'm at x equals 2, and I'm moving from right to left. I'm here at about 1.5, and going from right to left. And I just follow this up, right? I'm moving to the left, and I kind of have to track with the graph. And the point, it keeps going up and up and up. The y-coordinate is getting larger. Y is tending to go toward infinity. If we had more graph and we kept following it, this dashed line would keep doing this. Give me a second. Dashed line would keep doing that. And then this line, I'll try to draw it carefully. That was pretty terrible. We'll try once more, and whatever I come up with is good enough. Good enough. It'll just keep going, right? So we're going to say that the y-coordinate goes to infinity because the y-coordinate just increases without limitation. The only visual limit is, well, how much of the graph did you tell the computer to make? And if I was able to go back and redo the graph and do more vertical space, more up in the positive direction, well, I would get more graph with this trend of the blue graph getting closer and closer to the black dashed asymptote. This is a rational function. Hopefully you remember the term asymptote from before. I'm pretty confident. I can double check right now, but I'm pretty confident. Properties of rational functions. Yeah, we did that. Okay. So the way I can write that using a limit is the limit as not 1. The limit as x goes to 1. What's the what's it going to be? If it's not negative from the left, it's from the right, it will be positive. So that superscript plus sign means that x is going to 1 from the right, from the positive direction, or from positive infinity, of 1 over x squared minus 1. This equals infinity. Okay, so these are the two one-sided limits, which we can now, if it will let me, we can see them both. And the point I want to make is that the right-hand limit and the left-hand limit are not the same. We got two different results. We got plus infinity, and then we got minus infinity. So basically, this means that the two-sided limit, the one that is not from the left or from the right, but just what's the limit, what should the function be doing, doesn't exist. We get nothing. So we'll say that the limit as x goes to 1 of 1 over x squared minus 1. I'll just write d and e. Some people will write equals d and e, which is fine. I guess it does not exist. Just to me, it has two verbs. So anyway, I'm leaving out the equals for that reason, but it's not super important. You could write equals, and whoever's reading it will know what you mean. Okay, so that's basically a one-sided limit. And then also, this is our first example, at least for the stream, doing this visually. We're about 40 minutes in, and I had planned on doing at least an hour, but I definitely want to do at least one, probably 2, maybe 3 examples of using a limit to find a derivative. But I have to talk about rate of change a little bit in order to do that. So that's what we're going to do next. We're going to do rate of change, and I'm just going to skip ahead. There's a bunch of visual examples here. I'm just going to skip them, and I want to get to rates of change. This is a bit long-winded, but this is basically I wrote this up so that a student could just read it, and then before class, like right, I expect the student to read before class. Very idealistic of me. But I wrote it that way, that someone could just read it. So I'm basically going to walk through this, and then we're using a limit. I'll talk about this a little bit more, and then we'll do a couple of examples of finding rates of change, and then we'll get to finding derivatives, which is very similar. And that's going to take more than an hour, though. That's probably going to be like an hour and 20 minutes or an hour and 15. Okay, so average instantaneous rate of change. So the way you should think about an average rate of change is that if you're driving somewhere and you don't drive at the same speed the entire trip. If you drive on surface streets in your neighborhood a little bit to get to an on-ramp, well, you're not going to be driving 65 miles an hour on the surface streets, right? Assuming you're following the speed limits that are set. Even if you exceed them a little bit, 65 would be kind of a lot for a surface street. It would be totally unsafe. And when you get on the highway, you're probably going to go 60, 65, depending on where it is, 70 at some points, depending on where it is. So the average rate of change, your average speed in a sense, would be, well, what's the total distance traveled divided by the total time it took to do the traveling? And you would find that, well, it's not going to be, say you're driving from here to Austin, right? It's about 80 miles or so, and it's going to take you, a little over an hour, depending on if you want to count it as, oh, I've entered the Austin city limits, therefore I'm in Austin. My trip is done, so to speak. Or, well, no, I have a destination in Austin. That adds more time, especially when you exit the highway and you get on Surface Street. Or if you try to go to Austin, during, I don't know, not at 3 in the morning and you have to hit traffic, it's going to take a little longer to get where you're going. But let's say that your whole trip takes an hour and 45 minutes, right? And you traveled about 85 miles total. Well, what was that going to be? 145. I'm sorry, not 145, but 1.75 hours. 1.75 hours, right? That's going to be my denominator because it's miles per hour. And I traveled 85 miles, right? Well, what is that going to be? I don't have a calculator to hand, so I'm going to go grab one real quick. Okay, so while I was getting this, I realized, this isn't that hard. I probably could have done this without a calculator, but fine. I've gotten it. We'll just do that. So I get 48.57. I think that's a pretty good estimate. Right? 85 miles is about right. An hour and 3/4. If you run into traffic or something, you're going to go a little bit slower overall. And then you had some surface street traveling. And, most of your trip was not spent going exactly 48.57 miles per hour. You were going 30 or 35 for like 30 minutes worth because you had to get you surface streets to get from your house to the highway. And then when you got to Austin, from exiting the highway to get to your destination, you had to use surface streets again, potentially in some traffic. So maybe you're going like 20 or 25 miles an hour for parts of that. And then on the other end, on the freeway, you're generally going to be going, well, anywhere between 60 and 75, right? And there's a section, I'm pretty sure, between San Antonio and Austin where 75 is the speed limit. So most of your trip will not be spent at this average speed, but that is the average speed you were going. It's just, over a long time period, it's not very reflective of individual speeds at individual points in time because it's an aggregate of a long period of time. And 2 hours is not that much, but when you're considering your speed, like the speedometer on your vehicle, that's measuring the average speed over a very short period of time. The speedometer, I would imagine older ones versus more modern ones would operate differently, but your speedometer probably, I don't know this for sure, I probably should have looked this up ahead of time, but your speedometer might be doing this. It might be recording your distance traveled at certain intervals. The computer knows how far you're traveling based on a calculation based on the revolutions in the engine and the rotation of the axle, right, the drive shaft, and there's a calculation involved. The computer does that. Older ones are probably just a physical connection to the drive shaft, counting the number of turns every second or something like that. But then the estimate is done over a very short period of time, so it gives you an accurate, this is how fast you're going, right? But it's still an average. Almost certainly, if the computer is doing it, it's an average, I would imagine. Could be wrong. It might have a real-time calculation that's merely a calculation based upon the rotation of the drive shaft. It could be. I'm not sure about that. But it's over a short period of time, so it's accurate. But if you're just recording distance traveled, well, that's not going to be accurate down to an individual speed. It's just the aggregate. Anyway, I've yammered about that enough. You can think about this in terms of the rate of change in a function, not necessarily the speed of an object, which it is an average rate of change. But, I'm sorry, the speed of an object is a rate of change. But we can also ask about the rate of change of a function. And that will lead us to derivatives. So the average rate of change of a function is the slope of the line segment from, if you're finding the average rate of change over an interval. So from A to B, right, you have this function, you have an interval, a starting point, and a stopping point. So you have something, I already have a drawing there, but I'll make a new one. You have something like this. Here's A, here's B, right? Here's a starting point, here's a stopping point. This is f of A, this is f of B, and the line segment between them, that slope, that is the average rate of change from one point to the next. And if you think about slope as rise over run, right? We usually use m for slope. The difference of the two y coordinates, well, that's going to be f of b minus f of a all over b minus a. Right? That's the slope calculation. Well, that's exactly what we're going to use over here. So let's say I have this function f of x equals x squared, and we're going to be talking about the interval 1 to 5. Using the slope formula, oops, I could start with this, let me do this. This seems to help for reasons that aren't clear to me, but it seems to help. Just y2 minus y1 over x2 minus x1. That's the standard way of writing the slope formula. Well, the numerator, I don't have to write these as y variables. I could say, well, y2 is f of x2 and y1 is f of x1, so I can write it like that. And then I can put in the numbers, and I can total that up, and I get 6. And that's just using the slope formula, fairly straightforward, I think. Well, what if I wanted to do this differently? And there's a reason to do it, which we'll see soon enough. But there's a different way to do it. The difference quotient is a way of writing the average rate of change in a different format, but really it's the same thing. So instead of doing a calculation with the beginning of the interval, the a value, which is 1 in this case, and the end of the interval, the b value, which is 5 in this case, instead, and for reasons that I will explain when we get closer to needing to know, instead of referring to a beginning point and an ending point, we can instead we can talk about the beginning and then the length of the interval, right? Like if you ask someone, how long is this thing going to last? Then they go, from 1 to 5 p.m. You know that it's 4 hours. They didn't tell you that, you just knew right away. And if you ask the same question, how long does this thing last? They go, it starts at 1, it lasts about 4 hours. You would know it ends at 5. It's the same information, not directly said, but implied. That's the difference we're going to be using. Instead of giving the starting time and the stopping time, we will instead give the starting time and the length of the interval. Why are we doing that? Well, we'll see why soon enough. So we're going to call x1 the beginning of the interval, which I was also calling a, but in this example, it's x1. We're just going to call it x. We don't need the 1. And the reason we don't need that is that instead of using x2, we're going to make the assignment that h is x2 minus x1. H is the horizontal distance from one point to the next in the interval that we're talking about. It's the width of the interval, or the length of the interval, if you want to call it that. Well, if we do that, then x2 is x plus h. And I don't need to talk about x2 anymore. I can just talk about x plus h. So if I do that, and here in this formula, I start the same way that first one did. I replace the y's with f of x. In place where I have x2 here and here, I'll replace that with x plus h. And in place of x1, which I have here and here, I'll replace with just x. So I'm referring to the beginning of the interval and the length of the interval rather than referring to the end of the interval. And when I do that, I get this. I get f of x plus h minus f of x, and on the bottom, x plus h minus x. Now you notice on the bottom, I've got a plus x and I got a minus x. There's an implied. It's when you don't have a plus in front of something, it's implied as a plus. It's being added somewhere. That means that those x's can cancel, and I end up with this thing, which is called the difference quotient. F of x plus h minus f of x all over h. It's called the difference quotient. It's equivalent to the slope formula. It's just a different way of presenting it. So in our example, if we wanted to use the other version, this difference quotient version, well, we started with x1 equals 1, x2 equals 5, and that's going to translate into x equals 1 and h equals 4. Okay? Now, I don't need to do this necessarily in the way I'm about to, but this is going to be this order of doing the algebra is going to make later problems easier. So I'm going to do it this way here. So f of 1 plus h, which is going to be 4 later, but we're not going to put it in yet for reasons I'll explain. Well, when you are substituting into a function, we have f of x equals x squared. That's our function. So f of 1 plus h, remember x is 1, right? And I'm putting in the 1 now, but not the h yet. Well, this is just that whole input squared, all right? It's not 1 squared plus h after the square. It's 1 plus h, that whole thing as a group, squared. Which that's basically 1 plus h times 1 plus h. You can FOIL that, and you total that up, and you get 1 plus 2h plus h squared. That's f of 1 plus h. On one note, you can do it. So when I go to build the entire difference quotient, okay, I replace f of 1 plus h in the difference quotient with 1 plus 2h plus h squared, which that's what I calculated. And then, I have this 1 and this negative 1 here. Those will cancel. So I have 2h plus h squared over h. And here's the key part. The goal here, well, I'll cut to the chase and sort of break the, normally I wouldn't say this at this point, I'd put it off to later. We're going to end up using a limit for this, and we're going to end up putting in a 0 for h at some point. So having h on bottom is not a good thing. We're going to be doing that soon enough. So in the numerator, I'm going to factor out that extra h, and now these two h's can cancel, and I just get 2 plus h. And I want you to think about what we have here. I have a formula that gives me the average rate of change for this function starting from 1 and going till wherever. If I put in 4 for h, I'm going from 1 to 5. If I put in 10 for h, I'm going from 1 to 11. I get to decide the length of the interval after I've worked out the formula for it. I don't have to have a number for h at the beginning. I can put it in later. That's going to become important when we try to use a limit for this. So this just summarizes what I've said. The average rate of change is, if we plug in 4, we'll have 2 plus 4, which equals 6, which is, of course, the number that I got earlier. You get 6. 6 is that average rate of change. But the benefit of doing it this way is I got to choose the length of the interval afterward. Now, there's something that I'm going to kind of go through quickly, but you might ask, okay, that's fine, but we were saying we're going to do an interval from 1 up to 5, but because I have h involved, what I can do is I could say, well, I'm going to start here at 1 and then go here to 3, and I want to find that average rate of change. Well, I'll just put in 2 for h, right? But that assumes that the interval begins at 1 and ends somewhere after, to the right of 1. What if I wanted to start the interval at 0 or negative 1 or negative 10? What if I wanted a segment more like this? I wanted to know this average rate of change. How would I do that? Well, it's basically the same process. In the document, it's not written. It's not drawn out. There's no diagram, but the algebra is the same. if you want to choose your h to be negative, which kind of seems weird that you would have a length being negative, but the reason we can do that is this. Think about it this way. If you're driving in your car and you put the car in reverse, you could say that you could claim that your velocity is negative because you're moving backwards. You might even say that your speed is negative if you wanted to be, you didn't want to be careful about the terminology. Oh, my speed's negative because I'm moving backwards, right? You could say that. Since we're doing algebra within calculus, we have a coordinate system, and there's a positive direction and there's a negative direction. And when something moves in the negative direction, we'll say its speed is negative. Well, I'm sorry, we will say its velocity is negative. Speed is the absolute value of velocity, but I'll say the velocity is negative. It's moving in the negative direction, therefore velocity is negative. So what we have to do is say, well, that means a distance can be negative. If a velocity can be negative, a distance has to be negative potentially as well. So we'll say this. If you have a number line, okay, and I'll put 1 here and I'll put 5 here. If you're measuring forward, you're getting a positive distance measure. If you are measuring backward, you get a negative distance measure. So h can be negative if we always make sure we're talking about measuring distance from some central point, and we're measuring left, we're measuring to the right, we're measuring in all directions, and half of those are measured as negative numbers because one direction's positive, one direction's negative. So some of those measurements we're going to call negative. Hopefully that kind of makes sense. It seems counterintuitive that you can have a negative distance, but we're not talking about distance. We're talking about the measurement of that distance. And since we have a coordinate system, there's a negative direction. And measurements done in that direction, we're going to call negative. Okay, so if you work out the algebra there, if we have some interval that goes from 1 plus h to 1, remember h is negative, so this 1 plus h is less than 1 because h is negative. H is negative 8, right? So we're going from negative 7 to 1, right? If you work out the same calculation, and you can pause the video, or if you watch it, if you're the one person watching it now, you can watch it back later and pause it and read through it and just check that it's correct. It should be. You get the same formula, 2 plus h. So intervals starting with 1, their average rates of change are all going to be 2 plus h. And intervals ending at 1, their average rates of change will also be 2 plus h. So why can't I just say that the average rate of change for an interval beginning at 1 or ending at 1 is 2 plus h? Either one will use the same formula. So I want to look at a numerical example. Well, I'm considering skipping it because we're running up on an hour, and I don't want to go to an hour and a half. That's a bit long. So I'm breaking the suspense there. I'll just say, let's go ahead and do it. It won't take that long. If I look at this interval from negative 1 to 1, the length of the interval is 2, right? But it's ending at 1, so I'm going to call that negative 2. Okay? The length is 2, but it's ending at 1, therefore I'm measuring it backwards, negative 2. This one here is negative 1, negative 0.5, stray mark there, negative 0.1. If I apply that formula of 2 plus h, I'm just adding 2 to each of these values. So this is 0, this is 1, this is 0.5, this is 0.9. Okay. If we go to the other side, what's the length of this interval? Well, it's beginning at 1, so it's positive. It's 0.1. And then 0.5. And then 1, and then 2. And if I look to find the average rate of change for each of those, I'm just adding 2 because that's the formula. Add 2 to h, and you get the average rate of change. So this will be 2.1, this will be 2.5, this will be 3, and this will be 4. And if I look at these numbers from right to left, 4, 3, 2.5, 2.1, it kind of looks like it wants to go to 2. That's the output I'm seeing, right? And then these numbers here, 2, 1, 0.5, 0.1. It kind of looks like 0, maybe, is what that wants to be. Now, if I go look at the left, I can go, okay, looking at these numbers first, -2, -1, -0.5, -0.1. They look like they're going to 0. They want to be 0. Oh, these two guys agree, 0. So 0 is what I'm trying to do. If I'm thinking about a limit, h is going to 0 as I look at these different intervals. If I look at it from intervals, that are small versus large, well, I've written them. I've written them in the order that h is going to 0, because I'm starting with a larger interval and shrinking the size of the interval as I go towards the middle of the table. Here, if I look at these numbers, well, 0. Oh, I made a mistake. Yeah. Here I added 2. -2 plus 2 is 0. Probably someone has noticed this already. -1 plus 2 is 1. -0.5 plus 2 is not 0.5. It's 1.5. And -1 plus 2 is not 0.9. It's 1.9. So let's fix that. So 1.5, 1.9. That took a while to notice. If you look at these numbers, look at the pattern, 0, 1, 1.5, 1.9, it kind of looks like this is going to 2. Which these agree. So, yeah, 2 is that limit effectively. So I'm getting that the average rate of change at 1 is apparently 2. And we're going to call that instantaneous rate of change rather than average rate of change, because at the point 1, there's no interval. There's no length to the interval. If h is 0, oops, sorry. If h is 0, well, there's no interval because the length is 0. Okay, so this is a diagram that basically shows those segments. I'm going to skip that. Each of one of these red segments corresponds to one of these intervals, but I think the point is clear. We're going to find the limit as h goes to 0 of the average rate of change formula. So the limit as h goes to 0 of 2 plus h. That's the rate of change formula. Well, 2 plus h is a polynomial. Even though x is not present, x is not the only variable you can use. A polynomial is about the arrangement, not the symbol used. If we had 2 plus x, that's a polynomial. That looks like one. 2 plus x, that looks like a polynomial. Just because we're using h doesn't mean this is no longer a polynomial. It's just not using x. So I can plug in the 0 and get 2 plus 0 equals 2. I'm just applying a limit, really. Okay? And we're going to call this the instantaneous rate of change of the function, and it's the limit of the average rate of change. So the instantaneous rate of change equals the limit as h goes to 0 of f of a plus h minus f of a over h. That's just a definition we're going to use. And this is going to help us find derivatives, basically. And I spent a lot of time going through the nuts and bolts, which, it's not very, very important to understand all the details of this. I just want you to know, I want you to understand what it is on a basic level. If someone asked you, what is a derivative? You could give them a pretty good response. Oh, it's a calculation of the rate of change in a function. Okay, yeah, that's a derivative. I want you to understand that. And I'm just hoping that by explaining these examples that becomes fairly clear. Anyway, let's go find something a little more tangible. Well, I'll just work this one out. And then we'll go look for one that instead of having at x equals 2, find the instantaneous rate of change in a number, I want to do at least one where we're finding the derivative of a function rather than just the rate of change at one value, because basically the derivative of a function gives you a new formula that will give you any of the instantaneous rates of change that you want by plugging in the x-coordinate of the point that you care about. But we'll do one that's with a number, 2 in this case. So what we're looking for is we want the limit as h goes to 0 of f of, well, x plus h, but x is 2, so I'll put 2 plus h, 2 plus h minus f of 2 all over h. And there's several ways to do these kinds of examples. H, not x. There's several ways to do these kinds of examples, and I'm just going to do the way that I would normally write it. You can deal with the numerator first and get the numerator set up and simplified, and then worry about the whole limit. That's something you can do. I'm not going to do it that way. I'm just going to write the whole thing out. So this is the limit as h goes to 0. That's an h9n. H goes to 0. Well, I'll do part of it over here. F of 2 plus h is equal to 1 over 2 plus h. It's not 1/2 plus h. It's 1 over 2 plus h. The 2 and the h are a group together inside the function. So this is going to equal 1 over 2 plus h minus f of 2 is, well, 1 over the input, 1 over 2, all over h. This is written kind of small, so I'll zoom in. So this might look kind of imposing. There's a lot going on there that is not necessarily easy to deal with. But hopefully through the material on rational functions and solving equations, you kind of got how to deal with this. And there's two main ways, and I'll show the way that I prefer that I think is more straightforward. The material probably called this a complex fraction. I don't like that term, but that's probably what you read it as. I would call it a nested fraction. There's a fraction inside of a fraction. And that's complicated. I don't want to deal with it. I want to simplify this and write it with fewer symbols. And I don't want to have fractions inside of fractions. So these two little denominators have to go. They have to move or cancel or something. You got to get them out of their current location. And the way to do that is to multiply the top and bottom of the big fraction by the product of those two little denominators. So I'm going to multiply top and bottom by 2 times 2 plus h. And since I'm multiplying the same thing on top as I am on bottom, I'm not really changing anything because this multiplier I'm writing here is effectively equal to 1. So that I haven't changed anything because this guy equals 1. Okay? So I'm going to distribute this, and this guy is going to distribute and show up in the numerator there and in the numerator here. This guy is just going to get written next to the h. I might write it as 2h. Maybe I'll put the h between those two factors. The order doesn't really matter, though. Okay, so this is going to equal the limit as h goes to 0. So I've said before, and I think it's quite true, that calculus is 85-95% of algebra. Do you understand algebra fairly well? Do you have a pretty good grasp of it? You remember it? Not only are you able to effectively use algebra, but recognize what algebra to use. So there's an example of that. If once I pointed out, you probably thought, oh, okay, yeah, that makes sense. Ideally, before I wrote it, you might have thought, oh, we're going to have to use a fraction of something over that same thing at some point because we're dealing with algebra, basically. So if you recognize that, that's great. And if not, well, now you've seen it again. Maybe you'll recognize it next time. So this is going to be 2 over 2 plus h all over 2 plus h minus 2 times 2 plus h all over 2. I hope my writing's pretty clear. All over h. And we get a bunch of cancellation. The 2 plus h here and the 2 plus h here, this 2 and this 2. So the little denominators are going away. That's why I wanted to use this multiplier, to get rid of those little denominators. It's not the only way to do it. So if you had a different method in mind, as long as it works, then that's fine. So this is going to be the limit. I'm probably say gonna be a lot. Maybe I should stop doing that. So this will become 2 minus 2 plus h all over h. So in my numerator, I'm going to distribute this minus sign in front of the parentheses. So this is the limit as h goes to 0 of 2 minus h all over h. Now those 2's are going to go away. Right? 2 minus 2 is 0. So this will be the limit as h goes to 0 of negative h over h. And just think of it as being x. It behaves the same way. We're using h primarily because we're thinking about the horizontal distance from one endpoint to the other. And also, the next example we're going to do, well, x will already have been used as a variable. We can't use x at the beginning for this. We will not be able to use x here. It won't work because we're going to have already used x for something else. You don't have to use h. You could use s or v or p or whatever you want. You just have to pick some other letter. And I'm using h because this is the horizontal distance from one point to the next. So, of course, negative h over h is negative 1. So this is the limit as h goes to 0 of negative 1. And I'm using parentheses because whenever you have a negative, basically, if there's anything else in front, you're probably going to end up using parentheses. There are exceptions, but that's basically the reason I'm doing it. The limit is being applied to the 1. So if I wrote it without the parentheses, this is a bit pedantic, but if I wrote this, it looks like limit of nothing minus 1. So it's just more correct to use that notation. Anyway, that's just going to be negative 1. The limit of a number is just a number. The h does not affect the value because negative 1 is just negative 1. If h is 30, negative 1 doesn't change. So there's our solution. Negative 1 is the instantaneous rate of change of that original function at x equals 2. So I'm going to go ahead and find one that, let's see. Let's do this. We need to think about tangent lines as well. So we're going to do 2 more examples. I'll try to wrap this up in the next 17 minutes I will aim for. So if you know about some geometry, let's say you have a circle. Let's try to get, we'll call that a circle. Hold on a second. A line that, let's say this, a line segment through the center of a circle. This is called a diameter, right? A line segment that is not through the center is called a chord. A line segment that goes through 2 places, not segments, right? A line. So this is not a segment. This continues indefinitely on both sides. A line that goes through twice is called a secant line. And then if you have a line that goes, touches the circle, not goes through, but touches the circle just once at a single point, this is called a tangent line. And anytime you have a function that you can find the instantaneous rate of change for that function, you can form a line that has that instantaneous rate of change as its slope and goes through that point. That's called the tangent line. So if I make up some graph like that, right, that's some function. I don't have coordinate axes drawn, but you can put them in mentally wherever you would like to. If I have a line, let's not do that one. Well, let's do this. If I have a line that hits that function at one point, and in fact, let's do this. Let's throw some axes on there. If this y-coordinate is a, I'm sorry, the x-coordinate is a, and the y-coordinate is f of a, all right, then this point here is a comma f of a. And the slope of this line, we're going to call the derivative of the function at this point. It's the instantaneous rate of change, but I'll go ahead and use the derivative notation now. F prime of a means the instantaneous rate of change in the function f at the x coordinate a. All right. Instantaneous rate of change of f at x equals a. That's what is implied, but just that little mark there tells you, oh, this is not f of a. This is instantaneous rate of change of f at a. Okay, so that's basically what this is talking about here, but just not in a drawing, but in text. So I'm going to skip this one. We could use it, but I'm going to do this one instead. Find the line tangent to g of x equals 1 over x at x equals 2, and we're going to be reusing the example we worked out. We already found that g prime of 2 equals negative 1. Is that what we found? Oh, maybe this is not the same one. Let's go look. Yeah. Hold on, I'm just suspecting that I've made an error. That's all. Hold on a second. Just getting suspicious. Occasionally I'll get the feeling I've made an error, and I don't see it right away, but I'm thinking, but there's got to be something. Let me double check something real quick. I definitely feel like I made a mistake. But I don't see what it is. Well, there's one thing, but this is very minor. So you might have noticed I used G here, but then I called this F. That's not that big of a deal. It doesn't affect the answer that I get, but I'll go ahead and fix it. I just feel like I should be getting some other number besides negative 1 here. It just seems like there's an error, because I really ought to be getting something more like negative 1/4. It just seems like I've used the wrong number somewhere. Oh, I see it. That was silly. Now, no one's typed in the chat, oh, you forgot to do this and this, so maybe no one's noticed. Does anyone notice now? I'll wait a few seconds. I think there's one person watching. I'm not 100% sure, though. I have to wait at least 12 seconds. I think that's what the delay is. No. Either no one watching or no one chiming in to say what the mistake is. So when I multiplied top and bottom by 2 times 2 plus h, I forgot to write that down in the next line after it. This didn't make its way to the next step, so that's embarrassing, but we'll just fix it. So 2 times 2 plus h. So here, let's put the 2 in front, which I even commented that I might do that, and then I immediately forgot to do it. So we'll do all this. So we do not get negative 1. What we get when the h's cancel is we get negative 1 over 2 times 2 plus h. And we're finding the limit as h goes to 0. So if h goes to 0, I can just plug that in. So negative 1 over 2 times 2 plus 0. Well, there we go. That's going to be, or it will become negative 1/4. So there we go. That's the correct slope. Sorry about that. So when we go over here, not negative 1, negative 1/4. Okay. Okay, so I have a slope that I want to use, and I have it implied in ordered pair. If x is 2 for the point we're dealing with, then y will be g of 2, which will be 1/2. Okay, so I'm going to use the point slope form for a line. So y equals m times x minus x1 plus y1. The x1, that's the 2. The y1, that's the 1/2. Okay, and of course the m, that's negative 1/4. Okay, so y equals negative 1/4 times x minus 2 plus 1/2. So that's negative 1/4 x plus 1/2. 1/4 times 2 is 1/2, and the negatives, double negative becomes a positive. Plus 1/2. So I get y equals negative 1/4 x plus 1. That's my tangent line. So this is the line with slope equal to the instantaneous rate of change of the function at x equals 2 that only touches once. Now, depending on the shape of the function, it might actually touch twice, but it's not going to do like this, where there are 2 points close to each other that touch. It's going to do like this one, where there's just the 1 point of contact. Okay. So what I want to do now is I want to, just to confirm this is correct, I want to go look at graphing this. And sometimes it's a little tedious to type this in because, yeah, that comes up every time. Okay. I'm going to make an adjustment here. Okay, that will just let me type it in, I think. Yeah. Okay, so 1 over x, and then this one, y equals negative 1/4 x plus 1. And you can see, if we get rid of this stuff, that these 2 points, or these 2 lines, or curves, or rather I should say, touch just at that 1 point, right? The orange graph, that is the function itself, f of x equals 1 over x. And then the purple line is the tangent line. If we zoom in a bit, you can see that after a little while, these are pretty close together, and it becomes harder to tell which one is the straight line. Like if you forgot which one was which, orange versus purple being the function or the line, just visually, which one looks straighter? Now I know that the purple one is the straight line, but just visually, they look the same to me. They look so similar, I can't tell which one is straight, which one is curved. And if you zoom in enough, it becomes harder and harder to tell them apart until they kind of run into each other. Now, this is zoomed in a lot, right? Like each little grid mark is, not the large grid, the small grid is 0.001. So very, very zoomed in a whole lot. But that's basically one of the reasons that derivatives are useful, because they can be used as a replacement for a function sometimes, depending on what you're doing. Now, this one does not touch, the purple line does not touch the orange graph twice, although that's a possibility. If the graph were different, can I even point? Kind of. You can kind of see my pointer. It's possible to have a similar graph that's different, but then the left-hand side, hopefully you can see my pointer, is over here. You know what, let's just do this. I'll switch back to this. So it's possible to have a graph like this. Let's try to do it a little bit better than that. A little bit better. It's possible to have a graph like this, and then the tangent line is more like right here, right? And then there's this other point where the tangent line crosses the function, but it's on a different section of the graph. This still qualifies as being a tangent because it goes through that one point there. What would not qualify as a tangent is something like that, which crosses twice. That's not a tangent line. Okay, so there's an example of finding a tangent line. Let's go look for, we're running up on an hour and a half. I'll just look for a derivative problem, and we'll do one that's relatively simple. Here's the definitions, which you can pause the video and read. The derivative of the function is the instantaneous rate of change, which I've really already said. If a function, if the instantaneous rate of change limit does exist, you get a number that way. We'll say that the function is differentiable at that x coordinate. If f is differentiable at every point in its domain, we'll just say the function's differentiable generally without specifying where it's differentiable, because it's differentiable everywhere that you could try, because it's differentiable at all the input values. So the derivative of a function is the derivative, it's doing that thing again. We've already talked about the derivative at a number, f prime of a, so f prime of 2, for example. But if you want f prime of x, which this gives you a new function that can be used to check individual values afterward. So like if you were gonna, if you have a function and you just want to know the instantaneous rate of change at x equals 2, well, we've already really done that. You can do that. You put in 2 at the beginning, right? The 2 would show up here and here and here, and you work out the calculation, you get a number, right? But what if you wanted to check the instantaneous rate of change at a lot of input values? Would you want to redo that whole process every time? Well, no. You would leave that as a variable. So here we have x instead of a, and that's going to be left as x while finding the limit, and then we'll plug in x afterwards. So we have to deal with 2 variables at the same time. The process of finding this new function called the derivative is called differentiation. And the domain of this function, whenever you define a function, you should refer to the domain. The domain of this function is all of the x values that worked for the original, but also when the limit exists. So it's possible to have a function where its derivative, say at 2, is not defined. That can happen as well. Okay, so let's do an example of how do I find that. This one should be pretty simple. Remember, the derivative of a function is the rate of change in the function, right? This is a linear function. What's the rate of change in a linear function? In other words, what's the marginal cost of a linear cost function? Well, it's 3, right? So we're going to get 3, but I'm going to go through the limit definition of the derivative to find that. So f prime of x, this is going to equal to the limit, it's going to be equal to the limit as h goes to 0 of f of x plus h, no number for x, I'm leaving it as a variable, minus f of x all over h. Okay, so this equals the limit. I'm going to plug in what f is doing, limit as h goes to 0, of 3 times x plus h. Remember, when you substitute into a function, the x plus h is a group that doesn't get separated, so they're next to each other here in this expression with parentheses around them. The 3 is being multiplied against both, not just the x. It's a really common mistake to write this as 3x plus h minus 2, and the h is just h. There's no 3 with it. Well, that's incorrect. And it's a pretty common mistake, so watch out for that. Minus 3x minus 2. The reason I'm writing parentheses is it would be another very common mistake would be to just write this as, whatever, minus 2 minus 3x minus 2, and leaving that as a negative. But you're subtracting a negative, right? I'm subtracting f of x. F of x has a negative term as part of it. If I don't put parentheses, this is the wrong symbol. Because I'm subtracting a negative, I'm going to end up having a plus 2. That's very important for getting this kind of problem to go correctly. Obviously, I think everyone, pretty much everyone knows that if you put a minus sign in the wrong place, then you're going to get the wrong answer. But in particular, these problems, it's an easy mistake to make. Okay, so then I get the limit. As h goes to 0, I'm going to distribute and get rid of all the parentheses in the numerator. So I have 3x plus 3h minus 2 minus 3x plus 2 all over h. Well, the 3x and the minus 3x, those go away. The negative 2 and the positive 2, those go away. So in the numerator, all I'm left with is 3h. So this is the limit as h goes to 0 of 3h over h. And, well, then the h's cancel. So this is the limit, because 3h divided by h is just 3. So this is the limit as h goes to 0 of 3, which is 3. That's the derivative of the original function. So we can say f prime of x equals 3, which it's a boring function, but it is a function. The output is always 3. So f prime of 1, 3. F prime of 3, 3. F prime of 200,000, 3. It's not a very interesting function, but it is a function. Has inputs, has outputs. And that's basically it. Other problems will be more complicated. And I can definitely do this again before, let's see, when is, I need to look something up real quick. Or do I already have it open? Yeah. Sorry, I'm looking for there we go, the schedule for the course. So Module 7 is due on the 11th. So I can definitely do this again, either tomorrow or the next day. If anyone asks, I can do more examples. If anyone asks, you can email me. I could put this whole document on Blackboard, so you could go look for one and say, hey, can we do this one? Also, you could ask for problems in the MyMathLab, that you access through the Blackboard content. Yeah, but that's been an hour and a half, which I think is plenty. And again, certainly I can do more examples of this. I think this is kind of the hard part, because it's a multi-step problem. There's a lot that you can make a mistake on. The good news is that this is, to some degree, some of the hardest material in the course. What happens in Module 8 is, to some degree, simpler. The beginning of Module 8 is basically, here's a bunch of shortcuts that let us find these derivatives way simpler. So, for example, when you have f of x equals 3x minus 2, I said at the beginning, well, the slope is 3. So anytime you have a linear function, you don't need to go through all of this business to find the slope. The slope is, or to find the derivative, it's just the 3. It's the number in front of the x. And we're going to have other shortcuts. So how do we solve this problem more quickly and more easily and not have to go through all this limit business? The limit is why this is working, and you need to understand what the derivative is representing. But then when you go to do a calculation at some point, you want to be able to do it a little more efficiently. Anyway, I said that's enough, and then I kept talking. So I think I'm going to say that's actually enough. I'm just going to pause for maybe 15 seconds and wait to see if anyone wants to ask anything before I end the stream. You can type in the chat. You can send me an email. I'm going to wait about 15-20 seconds. Well, I'll wait 30 seconds, and then that should be enough for someone to use the chat and type, hold on, I have a question. So 30 seconds. Basically, once the time is at 1:35, which is 36 seconds from now, I'll end the stream.